Alright, so what is left now are the other two Maxwell's equations, right, which is Gauss's law for both charges, and since magnetic charges are not present or monopoles don't exist, the Gauss law for magnetic fields is quite straightforward, right. So we'll try to convert these into the differential form. Okay, so remember that Faraday's law and Ampere-Maxwell's equation, they lended themselves in the differential form using the curl operator. So now we'll see that we'll be using the divergence operator. Right? Okay, so we again take a small volume this time. So we have delta x, delta y, and delta z as the side lengths for this cube, right. So this is my rectangular coordinates. Remember, the origin is our point of interest x comma y comma z. So if you remember the integral form, it was the closed loop surface integral E dot dA was written as q enclosed by epsilon naught, right, for free space. So we are going to write this as a volume integral of rho times dV. Okay, so rho is now a charge density per unit volume, and if I were to integrate this charge density over a volume of interest over which the surface integral is evaluated on the left hand side, I'll essentially get the net charge enclosed, right. Let's not forget the 1 over epsilon naught. So I've just replaced q enclosed as an integral, a volume integral of the charge density, right. Okay, so now we are essentially going to evaluate E dot dA around this surface of this cube, right. So the cube has 6 faces, right. So for each of these faces we can evaluate the E dot dA, right. So for this closed volume, let us take the face A, B, C, D and E, F, G, H, right. So for the face A, B, C, D and E, F, G, H, right? For A, B, C, D, DA is quite simply, so it is facing the minus, so the DA vector is pointing in the minus x direction, Ex direction, and for EFGH it is pointing, so these vectors would be perpendicular to these faces and they would be pointing out of the volume, right? So those are the DA vectors. Right? So for ABCD it would be minus delta y delta z Ex cap, okay, and for EFGH DA is plus delta y delta z Ex cap, okay. So the left hand side, let's start with this. So remember, when I do the dot product with DA, all that will be left would be the Ex component, the other two components drop off. So I have Ex at x times minus delta y delta z and plus Ex at x plus delta x times delta y delta z, right? So for the two faces A, B, C, D and E, F, G, H, these are the two terms, right? Ex evaluated at x multiplied by minus delta y delta z plus Ex of x plus delta x, right? So the electric field in the plane EFGH would have incremented, right, to Ex at x plus delta x multiplied by the same surface area, but since the electric field is pointed in the direction of dA, we don't have the minus sign, right? So we've covered the two faces ABCD and EFGH, right? So similarly, you could do the faces CBGH, right, and ADEF, right? So you can combine all the opposite faces and you will essentially get so for BCHG, for that face I basically have Ey of y plus delta y, and since the electric field is in direction of Ey, this would be plus delta x delta z, and Ey of y minus delta x delta z, right, because the sign of dA and E are opposite. And then finally for faces CDEH and ABGF, so the top and bottom surfaces, we get Ez of C plus delta z times delta x delta y plus Ez of z minus of t. Okay, so this is the left hand side where I have evaluated the closed surface integral E dot dA, right, for a very infinitesimal cube of side lengths delta x, delta y and delta z, right. And on the RHS is quite easy, it's just 1 over epsilon, and then we have the volume integral of rho times dV, which is essentially rho times the right. So you assume that rho is evaluated at x, y, z, and then the volume is just delta x, delta y, delta z, right. So you assume that the charge density is uniform within this cube, so I can just take that rho as a constant and just multiply it by the volume, right, infinitesimal volume. So we'll do the same thing, we'll divide by delta x, delta y, delta z throughout the left hand side and the right hand side, and you will essentially end up with the relation Ex of x plus delta x minus Ex of x divided by delta x plus Ey of y plus delta y minus Ey of y by delta y plus Ez of z plus delta z minus Ez of z by delta z. This is equal to rho over epsilon naught. Okay, so you can identify each of these fractions as the partials, right. So rho over epsilon naught is dou Ex by dou x plus dou Ey by dou y plus dou Ez by dou z. Okay, so you can also write this using our new knowledge on using gradient operators, del. You can identify this as simply del dot E is rho over epsilon naught, right. So one can write in a very compact way the Gauss's law for charges, right, electric charges, by saying that if you took the divergence of the electric field E, it is simply the charge density at that particular location divided by epsilon naught. Okay, so fairly simple looking relation. The reason I am not too impressed about these analogies for divergences and curl using fluid flow is really I cannot use those analogies in understanding what does the gradient of E mean, right, because there is nothing flowing, right, the electric field is not moving or flowing in any direction, there is no magnetic fluids or electrical fluids, right. So those analogies kind of work well for fluids and is very pertinent, but it's very hard to move that analogy into electric and magnetic fields, right, because there's really nothing flowing. So we'll see that there's a much more richness to the divergences and curls later on in this course, right. So I think that is a much better perspective to understanding divergences and curls rather than the very simplistic views of fluid flows. Okay. So, if I were to ask you what is the last Maxwell's equations, and can you just tell me what is the point form for the Maxwell's equations for magnetic fields, right? The Gauss law for magnetic fields, it should be very easy for you. So, just by analogy, remember the last of the Maxwell's equations for magnetic fields, right, is the Gauss's law for magnetic fields, and this is essentially 0. Okay. So, the surface integral over a closed volume for the magnetic field is essentially 0. So, we do not even have this charge density rho and anything on the right hand side. So, it is just 0 on the right hand side. On the left, we see that the integral of E dot dA transformed itself to del dot E, right. So, we can readily say that this transforms into the differential form of del dot B equals 0. Okay. So, we have successfully gone through some rigorous mathematics of evaluating these integrals in the integral form of the Maxwell's equations, but we see that when you reduce these contours and surfaces to an infinitesimal volume, the same equations reduce to a point form, right, that are very readily expressible using these divergence and curl operators. So, in this slide I am just going to list down all the equations that we have derived, and this is the final set of 4 Maxwell's equations in the differential form, right. So, we started with curl of E is minus dou B by dou T, and then by association we said that curl of B is mu 0 j plus mu 0 epsilon 0 dou E by dou T. Then we looked at the Gauss law for electric fields, and those gave us 2 divergence equations for E and B, right. So, even now if you probably typed in Google Maxwell's equations, this is probably what you will see, right. While this was not introduced to you in high school, be very satisfied that these are just simple extensions of the integral form that you were taught, right. And those integral forms, when shrunk down to a very infinitesimal volume around a point x, y, z, transform themselves into these sort of vector equations, right, gradient based vector equations, and is a very compact form of writing all 4 Maxwell's equations, right. So, remember, in the integral form it was actually a integro differential equation, right. So, some of there were some integrals and there were some differentials, right. So, remember the times always occur as derivatives, right, whereas the spatial part came as integrals, right. So, it's what we call integro differential equations, where you have both integration and differential functions in that form. We have, in considering only the point form of Maxwell's equations, we noticed that it is completely in the differential form, right. Both the space and the time dimension are in the differential form. This is a much more convenient form of the equations, which lends itself to solving, right. So, if I were to take all these equations. Remember, all these equations must be simultaneously satisfied for the electric and magnetic field in any scenario, right. While I have used mu naught and epsilon naught, it indicates free space, but nonetheless, right, no matter what be the sources of J and rho that we have, the electric and magnetic fields in free space have to obey all four of these equations simultaneously, right. So, the job for us going forward in this course is to really understand these Maxwell's equations, and these point form of the equations lends itself easily to perhaps look at some cursory solutions to solving these equations, right. Thank you.